Okay, thank you for kicking us off, Megan. It was a great start, and it's a pleasure to be here as a member of the organizing committee. I just thought I would start very briefly with a map. You can find many types of these maps out there on water stress, and it's just broad strokes on kind of the United States, more the water-stressed regions of the U.S. versus Israel. Okay, and I did not pay attention. I think I just do this. Here we go. So if we start, we could say Israel and its scientists and engineers are the world leaders in seawater desalination. On the other side, we could say the U.S. and its scientists and engineers are the world leaders in potable reuse. Seawater desalination in the U.S. faced environmental and political challenges, but the tide may be turning a little bit. Maybe that's due to the cost of potable reuse being revealed a little bit more. I don't know exactly, but the tide is turning a little. On the other hand, in Israel, potable reuse has not been embraced, but I would say that they are very well known for their high-quality agricultural water reuse. And I think Avner threw out the number of 50% of their agriculture is watered with potable reuse or with reused water, high-quality water. On the other hand, the U.S. is known for extensive brackish water desalination, and both together have a distaste for the term drought. In the U.S., you'll hear it's not a drought, dry is the new normal. And in Israel, I found this quote after a more recent dry period. I think it was almost a couple years ago. And the writer said, "I'm not using the word drought because it's something the government decides and it has economic implications." So again, a distaste for drought, but also both sides really like membranes. In Israel, membrane treatment accounts for 97% of capacity. When I submitted this slide, I didn't have the official number for the U.S. side, and these numbers are again broad strokes, but in the U.S. the number is more like 91%. But in California, in particular, potable reuse regulations require RO processes if you're doing groundwater augmentation or reservoir augmentation. And so there has been some recent pushback with carbon-based systems, but I would say still in the realm of desalination and water reuse, membranes are heavily relied on in both places. And that's good because our session that's coming up now focuses on those membranes in particular, and membranes for seawater and brackish water desalination. So Moshe, do you want to say a few words?
Well, thanks for providing me the opportunity to co-chair this session. Indeed, those 4 lectures we're going to have in this session cover quite a nice coverage of different subjects that relates to seawater, improving recovery of seawater, of desalination of membrane-related processes related to improved recovery and improved selectivity of during membrane processes. And we're going to basically call for the first speaker. You want to introduce the first one?
Yeah. First. Okay. So I think we introduce all 4 speakers now. So the first speaker will be Roy Bernstein of Ben Gurion University. Roy received his BSc degree in chemistry and environmental science and his master's of science in soil and water sciences, both from the Hebrew University. He completed his PhD at the Department of Environmental Engineering and the Zuckerberg Institute for Water Treatment at Ben Gurion University. After conducting postdoctoral studies in Germany and Belgium, he returned to the Zuckerberg Institute for Water Treatment to establish his laboratory. His lab focuses on advancing material and polymer science, aiming to develop and improve membranes with specific properties for environmental and industrial applications, particularly in water and wastewater treatment and desalination. He combines fundamental studies on model systems with well-defined characteristics, as well as laboratory and pilot-scale investigations using real solutions to investigate membrane properties and optimize their performance for practical applications. And I think I'm supposed to go ahead and introduce, okay, and I'm going to go ahead also and introduce Shihong Lin of Vanderbilt University. Shihong is an associate professor in the Department of Civil and Environmental Engineering and the Department of Chemical and Biomolecular Engineering at Vanderbilt University. There, he directs a research group with a mission to advance aqueous separation processes to address critical challenges for sustainability at the water, energy, food nexus. Dr. Lin has received numerous recognitions, including the Excellent in Graduate Mentoring Award from Vanderbilt, the Walter Huber Prize from ASCE in 2023, highly cited researcher from Clarivet, the Paul L. Bush Award from Water Research Foundation, and the Young Investigator Award from the Chinese American Professors in Environmental Engineering and Science. And Dr. Lin is the current president of that organization. And I'll turn it over to Moshe. Okay.
Thanks.
Good. Sorry.
So I present Razi. Actually, I know Razi since his master degree when he did his master in Ben Gurion University under the guidance of Professor Vitali Gitis. And then he went to the Technion doing his PhD on membrane processes with Michal Green, right? He received his bachelor, as I mentioned, and also master from Ben Gurion University. Then he did his postdoctoral training with Professor Menachem Elimelech at Yale University. His main research interests are centered on membrane-based processes in water and wastewater treatment, with current research activities focusing on understanding the mechanism of molecular transport and selectivity in membrane nanopores. Pei Chu, from Professor Pei Chu from, I hope I pronounced this properly, from New Mexico State University. She's a professor in the Department of Civil Engineering at New Mexico State University and the research director of New Mexico Produced Water Research Consortium. She leads basic and applied research on water quality, water reuse, desalination, and resource recovery. The goal of her research is to address the critical water challenges in arid and semi-arid regions using non-traditional water supplies to enhance water sustainability and resilience. She was selected as a Leshner Fellow on Food and Water Security by the American Association for Advancement of Science, PESCO endowed professorship and C. Herb Award Family Endowed Interdisciplinary Chair at New Mexico State University. So that's the entire presentation of the speakers.
Good. So, Roy, you're up.
Thank you very much for the introduction and for inviting me here for this very interesting meeting. Today I'll present work on strategies for scaling reduction for high recovery inland, not effluent, inland desalination, which include effluent desalination and brackish water desalination, no seawater desalination, I apologize. And I think that I will start with an open question that I have about that, is what should the recovery ratio target be? We talk a lot about high recovery. It's easy for us because everybody can claim I have high recovery membrane, but I think it is important to understand what we should aim. It is a case specific, probably geographical specific, but I think it is important for us to know where should we go. So today I will present three, not two. In the booklet they say two. I tried to present three approaches. for scaling mitigation in order to achieve these high recoveries. So this is a scheme for water reuse today. There is the biological treatment, membrane filtration, ultrafiltration, desalination, some advanced oxidation process, and then water reuse. Our lab is focusing on improving this process by focusing on the UF and the RO desalination or NF desalination, and I'll present a work on this desalination step. So one of the main challenges in high recovery desalination is the fact that we can have approximately up to 80% recovery ratio, which means that we produce a lot of brine, which pose two challenges. One is the complex composition of the brine, much more complex than seawater desalination. And also because it is inland desalination, we are restricted with the possibilities of discharging it into the environment, and therefore we need to reduce it as much as possible. And the main reason for the low recovery, or the relatively low recovery, is scaling. Most of us are familiar with scaling, precipitation of springly soluble salt, which can be estimated by this equation, which is the product of the ion, the scaled ion divided by thermodynamic constant. Scaling can occur in the solution and then precipitate, or can occur immediately on the membrane surface, heterogeneous or homogeneous scaling. The main scalant, as we all know, calcium sulfate and calcium carbonate, for which anti-scaling are available, so this can be overcome to some extent. In effluent desalination specifically, we have calcium phosphate precipitation because of the high phosphate, and our group and also other groups have shown that among the different scaling of the different crystal form of calcium phosphate, the amorphous calcium phosphate is the one that precipitates first. In addition to that, we have another type of scaling with the silica scaling, more complex than this, and also it mainly occur in brackish water desalination, and I'll present a work on that as well in my third example. So the first approach that we try to study, it's a collaboration with Professor Oded Nir from our department and Shihon, is quite straightforward, integrating an adsorption step prior to desalination step. When we are talking about effluent desalination, there is an additional benefit of removing the phosphate, which is enabled to recover it. We suggested the following scheme: anaerobic MBR for the biological treatment, adsorption using granular ferric hydroxide, followed by desalination. The choice of anaerobic comes from two main reasons. First of all, it produces high-quality water, which makes it easy to remove and recover the phosphate. And in addition, the phosphate that in the feed in anaerobic system remains in the effluent. There's almost no removal of phosphate during this process, so we can recover almost 100% of the phosphate, unlike any other biological system. So I'll skip, of course, the anaerobic system because it's less important here. This is the water quality that we obtained after the anaerobic system. You can see that we had relatively high phosphate concentration. These were real wastewater that we just take from a wastewater treatment plant. We filtering them through the anaerobic system. We had relatively high phosphate, but we also added phosphate to have 30 ppm of phosphate all the time because we wanted to accelerate the adsorption step in order to have recovery, and we had limited amount of volume to play with. So after we got this water, we used this column experiments. We had the feed, it passed through the column, and we collected the permeate. And we measured the concentration of all the ion as well as the TOC during the process. And you can see here the normalized concentration to the initial concentration with bed volume, And what we could find is, first of all, we could remove almost all the phosphate during this process until the breakthrough with a relatively high amount of bed volumes. We also managed to remove calcium and magnesium, and also TOC, the organic matter in the system. These two are beneficial to reduce scaling and also organic fouling. However, it poses challenges when we want to reuse and recover the phosphate. Following this step, we did a regeneration step, and we ran the 3 cycle of this process. We used 2 washing steps, one with acid to remove the calcium, and then with sodium hydroxide to remove the phosphate. We noticed that in each cycle, we were able to recover almost 100% of the phosphate. However, the adsorption capacity reduces in every step, from 10 to about 5. This was attributed to 2 things. One is the solution of the granular ferric hydroxide, but also due to the not efficient calcium removal during the first washing step. This was noticed by the fact that when we did the calcium balance, we always did not close the loop. But this brings another interesting point, is that the reason that it was not very efficient is that we used only 1 liter in order to recover it, in order to make it more realistic, to produce as little waste as possible. We filtered about 200 liters in each cycle. And looking at the literature, we saw that not many people report the amount of water that is being used for recovery. And we think that it is a very important point, and we tried to make it more reliable. We didn't continue and we didn't investigate it further, but we think that the amount that we are using for the recovery in order to make it a real application is really important. So after that, we took a fraction of the water. We think that it is the challenging part, when the TOC and the calcium are high enough. And we desalinate the water. We desalinate anaerobic effluent that went through the column and did not go through the column. We used the filtration system where we kept the permeate flux constant in order to have the same concentration polarization throughout the experiment. But we did not return the permeate flux back to the feed. This, in fact, means that we filtered with increasing the recovery ratio all the time, because the concentration in the feed increases as we go along. And we call it an open loop. This is the water quality for the water that went through the adsorbent and did not go. You can see the differences are mainly in the TOC, in the phosphate, and also in the calcium. We filtered at pH 6 and 6.5, constant pH. We also did one experiment where we didn't keep it constant, but then we had very high scaling due to calcium carbonate, so we kept it at 6.5, and we used low pressure RO membrane. So in each filtration experiment, we got this picture. The red one is the transmembrane pressure that increases during the filtration experiment, what we measure. The black line is a simulated osmotic pressure that tells us what is the osmotic pressure at each recovery ratio. This is a model that was designed by Oded Nir that took into account the concentration at every point that we measured, not every point, every 5% recovery ratio where we measured it, and also took into account the concentration polarization of each ion on the membrane surface. And then we deduce this increased osmotic pressure with the pressure that we measured, and this is the increase in the pressure due to fouling, which is mostly scaling. So we did it for the two types of water, and the red one is the one that did not go through the adsorbent, and the blue one is the one that did. You can see that without going through the water, we started to have an increase in the TMP scaling, we call it, around 60%, whereas with the water that went through the GHF, it went up to 90%. Only then we start seeing scaling. At the end of the experiment, we obviously looked at what we have on the membrane. This is the inlet and the outlet of the membrane that went through the GHF and that did not. We measured it at a higher level than when we started to see the incline in the scaling, because we wanted to exactly know what we have there. So you can see, first of all, that we have much less scaling, and also we measured and saw that the membrane that used only the anaerobic effluent, we have the calcium phosphate, actually two types of crystal, but the membrane that was filtered with the water that went through the GHF, we didn't see any phosphate, but we saw gypsum, which tells us that perhaps by adding antiscalant, we can further increase it, we can further increase the recovery ratio and get perhaps to a higher level. What I show here is actually the calculation of the saturation, the solubility index that indicates that, but we also did SEM and XPS and verified that this is indeed this type of scaling. So to conclude this point, we think that this very simple approach is feasible. We still have problem with the adsorption step. It's still not efficient enough, but any type of absorption can be used here if you find something that's much better. And also, a real techno-economical evaluation is needed to understand exactly how efficient this process here is as a whole. The next thing that we are investigating is trying to develop a new nanofiltration membrane. And here we are focusing on desalination, but not for potable use, but for agriculture use. And we have three types of membrane that we can think of. One is a membrane with no selectivity to ion whatsoever, but high micropollutants removal. And this can be interesting for places like Israel, where I've never mentioned that the fact that the effluent is already at a very high quality. So the TDS in Israel is less than 1 gram per liter, usually even much less. I'll show you later some numbers. But perhaps in Israel, we don't need to desalinate the water if we are using it for agriculture, but we do need to remove most of the micropollutants. So this is a very interesting, in my opinion, line of research, but we are starting to go there. Another less realistic membrane, perhaps, but very interesting, is what we call a mosaic membrane, a membrane that can pass the calcium and magnesium. It's a pressure-driven membrane, I must emphasize, that can pass the calcium and magnesium, but do not let the sodium and the chloride to pass. Of course, here they should or should not, it's not important that it will be with high micropollutants removal. There is a conceptual model that was developed a long time ago by our academic and Charles Linder that help us to understand what the membrane configuration should be. But as far as I know, nobody was able to develop such a membrane. So what we are trying to do is develop a membrane that has moderate rejection for ion, but we call it a symmetric rejection, which means that all the ion passes at the same rate, more or less. And the idea is that it should also have high micropollutant removal, and the idea is that we do not need, obviously, to remove all the ions, but we want to maintain the main ion in the solution. So if we can remove 30–40% of them, we can get to high recoveries, but still get high-quality water. For this, we are trying to develop what we call polyelectrolyte complex membranes, which is a combination of positively and negatively charged polyelectrolyte at a complex, not a layer by layer or anything like that. I'll not go into the details, but we started with two polymers, and we mixed them together. Polymers, do not like to mix together, so we did some manipulation to that, and we managed to do that. Again, I'll skip all the characterization. I'll just show some results. So we have different ratios between the negatively and the positively charged polymers. This is the single salt selectivity and permeability of our membrane. And you can see that the NF3 and also NF4 and 5 have relatively similar selectivity to all ions, all salts in this case. But we chose the NF3 because the permeability, which was not high to begin with, was relatively fine for us. Then we filtered salt. We filter a solution that contained all salt together, and we compare it to a nanofiltration membrane. As expected for the nanofiltration, the phosphate and the sulfate are very, very high, which means that we expect to have very high phosphate scaling. Our membrane was not as good for the single salt, but this is often the case. But still, we had higher rejection for sodium and chloride and lower rejections to calcium and magnesium, and mainly phosphate, because this was the aim. So we took synthetic feed and we mimic the composition of what is expected to be an 80% water recovery based on the composition of effluent from the Shavdan, the biggest wastewater plant in Israel. Because the rejection of the membrane is different, so the composition of the solution is different, mainly the calcium and the phosphate. And you can see here during filtration the relative permeate flux of our membrane versus the NF membrane. As you can see, there is some scaling, but it is much less, so we believe that this is relatively good direction. We then took real water, again supplemented it with ions in order to mimic 80% recovery, and we saw the same picture, and we also saw the same picture with the selectivity of the ions. And then we also looked at the SEM images, and we saw that the polyelectrolyte membrane has much less scaling than ANF, and we managed to see that this is indeed calcium phosphate scaling by SEM, and also digesting the membrane and measuring the ion using ICP. So we saw that the ratio between calcium and phosphate is for amorphous calcium phosphate, as I mentioned before. So to conclude this part, we believe that this direction is very interesting. We also, I have to admit that we also measured micropollutances removal for 48 hours. After 24 hours, we had excellent selectivity. After 48 hours, zero selectivity. So this membrane needs to be improved for the selectivity for micropollutants, but this also tells us that in order to get the real performance of the membrane, we need to run it for long term. I think that in a very nice paper from 2004, many already mentioned it, about the diffusion of micropollutants, but I think that that people are not very, they don't look at that in detailed enough, so I think it is a very important point. The last research that I will present is anti-scaling and low fouling membrane using membrane modification, something that my group has been investigated for many years. In this research, we used anti-fouling polymers, mainly zwitterion polymers, but we graphed them as polymer brush. Polymer brush are polymers that are tethered to a surface in such a high density that they stretch away from the membrane. And this configuration, this structure, gives the anti-fouling properties, enhanced properties, compared to similar chemistry that is grafted not as a brush. In addition to that, the brush has some steric exclusion properties because pollutants that are at more or less the size of the brush density cannot penetrate into the brush. It is called excluded volume because there is some osmotic pressure. And if the modification or the layer is not in brush configuration, the same molecule can penetrate and reach the membrane. So in the last few years, my group has been investigated a lot on this topic. And we did it, Another important issue is the brushes can be in different configuration, and it can be linear, which is the simplest one. It can be cross-linked at a gel, and it can also be in a bottle brush configuration, as you can see in C. So in order to obtain brush, it's not simple grafting. We need to implement more advanced grafting technique. The main one is surface-initiated atom transfer radical polarization. I will not go into the details. I'll just mention two things which are important here. First of all, in order to implement that in membrane, we need to have a functional group, what we call an ATRP initiator, attached to the membrane. And in most membrane, it's not easy to attach this polymer, so you need some to play a little bit with the chemistry. It also requires inert environment, which is a challenge. No oxygen in the system, so this limits the application. But our work, many people, including our group, are trying to develop oxygen-tolerant system. So our first experiment on that was on polyamide membrane for RO. We did a two-step polymerization method. In the first one, we attached this ATRP, and the second one, we attached the ATRP initiator, and then we polymerized these polytwitter we call it pseudo-bottle brush because we graft polymer at the first step, but not as brush. So to have a real bottle brush, we need brush as the anchor and brush as the brushes on the side. But here we only have butter on the brush, so we term it pseudo butter brush, but it's not really important. We started investigating it with water with a composition that mimic 80% scale, 80% recovery of brackish water with respect to calcium sulfate, as you can see here, and this is what we got. This is the relative flux of a pristine membrane, the XLE, and membrane that were grafted and increased grafting time. What we believe is an increased coverage of the polyamide system and the membrane. And as you can see, the one that was grafted for 360 minutes did not have any scaling throughout 24 hours experiment in a cross-flow system. When we looked at the SEM at the end of this, we could see that the modified membrane was completely clean, whereas the XLE membrane had very clear scaling of calcium sulfate. Then we went to much more challenging scalant, which is silica. We did the same experiment, and again, our membrane had some reduction, but after a few hours, it remained very constant, and you can see here that we did not face any silica scaling. Again, the SEM showed us that we hardly have any scaling on our membrane. The last thing that we challenge our membrane with 90% brackish water, brackish water that mimic 90% recovery. We took real brackish water from a well next to the Midrasha, to Sde Boker, we increased by 10 all the ions that we measured, and also because we didn't have any silica, we also added the silica, and we measure it for, this is the composition, and we measure it for 7 days, and throughout the 7 days you can see that after 3 days the XLE was not, the permeate flux went almost to zero, where our membrane in the first days did not experience any scaling, and experienced very little scaling even after 7 days of filtration. And in the end, you can see that our membrane had some scaling, but very little, whereas the XL here, you see huge triangle or pyramids, which is actually calcium carbonate. So I will skip what we have with the UF. I'll just summarize that we believe that achieving high water recovery in effluent desalination and inland desalination is crucial. We think that target values are necessary. We also believe that there is the need to enhance the recovery ratio with respect to phosphate also with an incentive to have resource recovery under the framework of circular economy. There are different ways to achieve it, either integration of method, new or improved membranes. We strongly believe that everything should be tested with real composition, real liquids, and under, as close as possible, real conditions. And everything, as Megan mentioned before, have to be analyzed techno-economical and using LCA as well to establish realistical and achievable performance targets. And this is extremely important, but it has to be done in the right way. I'll just acknowledge the two students that made all this work, my former PhD student today, Dr. Eric Zimen. Hao Hang is just finishing his PhD. The technicians, collaborator from the Technion Guy and Slava, Shi Hong, and Oded, obviously, founding agency, and thank you all.
All right. So first of all, thank you very much for the opportunity to be here. It's really nice to catch up with old friends and meet new ones. So first, I have to apologize a little bit because I actually modified the scope of my presentation. It's a little bit different from the booklet. And I want to give an explanation, not so much apologetic, but actually provides context to the discussion. So when I was asked to talk in this session of seawater desalination, at the time it was not combined with brackish water, I really scratched my head, like, what can I talk about seawater desalination? I was not performing active research with immediate relevance to seawater desalination. So I gave a topic on LSRO and trying to look at how we can use that to enhance the water recovery of seawater desalination or deal with the brine of seawater desalination. But then when I tried to prepare the presentation, I asked myself, is that really a relevant process? And then we had a discussion with Amy and Tahi just over the breakfast. And I wanted to challenge myself to give maybe a more directly relevant discussion to seawater desalination. And also, I wonder why I was not working on seawater desalination actively. And my impression was that the community, of at least the junior folks, and Amy reminded me that I'm no longer junior, it's not really working that much on seawater desal. Like it's more about brine management or selective separation. And I think a big part of the answer is that seawater desalination is kind of a solved problem, right? So, and if it were not a solved problem, it would not be supplying a large fraction of potable water to Israel, right? So, however, and it's a solved problem, so the junior folks, they don't want to work on solve problems. It's not a nice word in academia because it means that your contribution is going to be incremental, as many frame it. But another way to look at it is that if you can make incremental improvement to a process that is widely adopted, your practical contribution can be actually immense. And that reminds me of a recent there's a recent X Prize called Seawater Desalination with a price tag of 120 million, mostly sponsored by UAE. So some people criticize that, right? Why do we, there's a better way to spend those money and all that. But then I think this is actually a business case, right? Because UAE itself spends $3 billion per year just on seawater desalination. If it can make a 5% improvement on the efficiency or on the energy efficiency or the operating costs, it can recoup that 120 million within a year, right? So today the question I'm going to ask is, where are the remaining opportunities to improve the already mature seawater reverse osmosis? So this is a very famous figure that many of you have seen. It's from a paper that many published almost like 14 years ago, like 13 years ago. The idea is that the energy consumption of RO has improved over the past decades, and now is approaching the limit, right, the so-called thermodynamic limit. There's a more recent paper from a Korean group providing a lot of nice data, talking about the specific energy consumption of reverse osmosis. And as you can see now, the energy consumption, including the pretreatment, is about like 3.5 to 4.5 kilowatt hour per cubic meter. So that's a huge improvement if you compare that to the 1970s, which was multiple times of that. So I want to give just a brief review of what are the milestones in technology development that we had made in order to get to this point. Right, starting from in the 1960s, Sidley Loop and Surirajan, they developed the cellulose acetate membrane. So Loop has a really strong connection to BGU, where many of you come from. And then in the 1972, there's the development of the TFC, the thin film composite polyamide membrane. The major contribution from this better membrane is they reduce the pressure, hydraulic pressure, to achieve a reasonable water flux, a water flux that is actually usable in real process. And the pressure is directly related to the energy consumption. So that's a huge improvement, making seawater desalination feasible. And then in the 1980s and the 1990s, there was a development of pressure exchanger. So the major contribution was to recoup the energy that is still in the pressurized brine. And that, again, bring a tens of % improvement in the energy efficiency of seawater desal. And that's kind of the seawater RO system that we are having now, right, for most of the major treatment plants. In recent years, there's some new developments that I personally feel exciting, mostly at the process configuration, right? You have flow reversal RO from Jack Guron, and then CCRO from also an Israeli Efrati, right? Ladev Efrati, and then also batch RO. But the impact of this new configuration on seawater desalination is still to be verified, right? So there are a lot of people trying all this in brackish water desalination, water reuse, trying to improve water recovery or reduce scaling and fouling, but not so much yet on seawater desalination. Now, very recently, Manny and collaborator actually published two nice papers, one on Nature Sustainability and the other very hot recently on Science on chlorine-resistant membrane, right? So can we actually, by leveraging these new types of membrane, to simplify pretreatment and reduce the cost of pretreatment? So that's kind of the what I see as the roadmap or the history of seawater reverse osmosis development. Now, why I only talk about seawater reverse osmosis? Because I think it's actually the technology of supremacy compared to all the thermal processes that we had before. And the theoretical kind of rationale behind it is actually quite simple to understand. If you look at this diagram, for those who work on RO, is something very familiar. On the y-axis, you have the water recovery. Y-axis is the kind of the pressure or osmotic pressure, And the curve there is basically the brine osmotic pressure as a function of water recovery. So for most seawater reverse osmosis process, you apply a constant pressure. So the energy you actually consume is just a rectangular box containing both the yellow region and the blue region underneath. So the minimum energy is the blue region underneath, whereas the yellow region, the area of the yellow region is just the kind of the driving force or the entropy generation. So by just comparing the area of these two regions, you can find that seawater RO is very efficient, right? So this energy efficiency is like easily above 50%. And so this is actually a paper that I published a few years ago where I'm looking at the thermodynamic energy efficiency as the y-axis, and then the x-axis is the Gibbs free energy of separation, basically how difficult the separation is, right? It's more difficult when you recover more water or dealing with a high salinity brine. And as you can see, RO processes in general, these are the gray circles, they are actually very close to the thermodynamic limit compared to some other electrochemical processes or thermal processes, which we used to use in the Middle East for thermal desalination before the emergence of RO. All right, so there's reason for its supremacy, right? So how can we further improve it? Well, actually, there's a question that I wanted to ask is why do we actually not minimize water recovery? Because if you look at this diagram, if you shrink this rectangle, right, to reduce the water recovery, you can actually further improve the energy efficiency. But we are not doing that. We are recovering water at about 50% water recovery. So why that's the case? To understand that, we need to look at how the entire seawater RO plan is designed, right? So basically you have water intake, and then it goes into the pretreatment, and then you pressurize the water and go into these modules. And then at the end, you also recover the energy from the brine using EDR. And within these modules or pressure vessels, you have multiple elements with spiral rung thin film composite polyamide membrane looking like this, right? So if we want to be a little bit more quantitative, we can look at it this way, right? So a stream going into the pretreatment, and it's going to split into two streams. One going into a high pressure pump, and that's most of the energy is spent. And then the other stream going into a pressure exchanger, a EDR, where it recoups the energy from the pressurized prime. And then you combine these two streams, it goes into an RO process. You recover some of the water as your product to permeate, and then the brine is directed to the pressure exchanger to recover the energy. So you can do the math and all that, but really the energy that you spend are in three locations. The high pressure pump, that's most of where most of the energy goes. And then you have the booster pump to further increase the pressure of the stream coming out from pressure exchanger, because pressure exchanger is not 100% efficient. And then you also have the energy costs and also the chemical costs for the pretreatment. So here, one way for us to simplify the analysis is that we can actually combine the chemical costs and energy costs and using a equivalent energy cost to kind of quantify the cost for pretreatment. So now the question becomes, how do we actually design a system that kind of minimize all this energy costs, including the chemical costs in pretreatment? Now, this equation is not to be understood in this in this presentation, but the idea is that if you just look at the red curve, which I showed before, that is kind of ignoring all the pretreatment and all the inefficiency of pump and pressure exchanger and all that, that indeed you want to minimize your water recovery because that would give you a high energy efficiency. But then you also have another curve, which is this dash curve here, that are associated with all this auxiliary loss that I just mentioned, including the pretreatment cost. You don't want to pretreat all 100% of the water and recover 1%, right? That obviously doesn't make any sense. So through experience, this is both empirical and theoretical, the optimum actually sits at about 50%. And that's where most of the seawater RO plant is operating. It's not super sensitive to the recovery actually for a region about like plus and minus 5%. So this is basically the state of the art. Here I assume a pretreatment energy cost, including chemical cost, of 1 kilowatt hour per cubic meter. So with this, I want to talk about using this framework. I want to talk about what we can do to further increase the energy efficiency or reduce the energy consumption of seawater RO. So the question is, are we really at the end of seawater RO innovation, right? So it has approached the thermodynamic limit, but that's a relative concept. Compared to 1970s, yes, we improve a lot, but if we can further reduce the energy consumption by, let's say, 20%, we can actually save a lot of energy, 1/4 of the Israel annual electricity consumption, just for the global seawater RO. But can we do that? That's the question. Now, I think we can. The first thing we can look at is actually the pretreatment. There are not a lot of literature that took a look at the pretreatment because maybe academically it's not the most exciting thing, but I would say that's a land of opportunities. So many recently published paper on Science, right, just like developing this very exciting new membrane that is chlorine resistant and also scaling resistant. Now, I'm not going to get into any details of this because I don't know too much about it, but the question I want to ask is, with these new membranes or any membranes we're going to develop in the future that are more robust, more resilient, right, and Roy just talked about another membrane, can we actually simplify our pretreatment? What if we can reduce the pretreatment energy cost or equivalent energy cost from 1 to 0.5 kilowatt-hour per cubic meter, or maybe even to 0.2? What's the consequence or implication of that? Well, it's not hard to find that out. We just plug that into the equation, right? So this is the kind of the benchmark case I just showed. The specific, the specific energy consumption is about 4. That is comparable to what we see from the treatment plants. And the optimal water recovery is about 50% to 55%. If you reduce the pretreatment cost to half, then you can actually reduce the overall energy consumption by about 25%, right? And you shift the optimum water recovery to a slightly lower value, about 45%. If you can further reduce it to 0.2 kilowatt-hour per cubic meter, which is very ambitious, I'm not sure whether we can get there, then there's the opportunity of reducing the SEC for the entire process by 43%, right? So while we're struggling to kind of improve the RO process itself, there's actually a really unexplored area for pretreatment. Maybe it's just because scientifically not so exciting, but the practical room for improvement is actually very significant. All right, so that's pretreatment. The second area, any opportunities for actually practical energy reduction of the RO process itself, including the pressure exchanger and all that, of course. So there are people who believe that there may not be much room to improve in this because it's kind of perfected. I used to think it that way. First of all, I want to debunk 2 myths. The first myth is that 2-stage seawater RO can actually save energy. If you perform a detailed analysis, it doesn't actually save too much energy. It saves a little bit, maybe still appreciable, but not exciting enough for us to really invest in it, right? So what is 2-stage RO? This is quite typical in like water reuse or maybe brackish water desalination, but people are not doing a seawater RO. So basically, you can apply a lower pressure to recover part of the water, and then you raise the pressure in the second stage to further recover more water. The principle is straightforward. The energy you save is basically the yellow region here. However, the way I just described it is actually not super accurate, because if you do that, the flux would not be the same. In order to maintain the flux to be the same using 2-stage, you have to actually give a little bit more driving force for both stages. So instead of now instead of the yellow area you saw before, it should be the yellow area plus that little like green area that is above the rectangle, right? So the energy saving is actually not so much. So empirical experience suggests that the saving is rather insignificant, and we will actually quantify that. The second myth is that ultrapermeable membrane can save energy. So also for many, about 8 years ago, they published this paper, and they're suggesting that it's seawater RO increasing the A value from 0.2 to 1 liter per meter square per hour per bar. That's kind of the breakthrough that we have achieved from the 1970 to now. Can save a lot of energy, 45% reduction. That has already been achieved. But further improving the permeability from 2, let's say, the state-of-the-art membrane, RO membrane, to 10, it's not going to help much. It only leads to 3.7% reduction. And that's actually true, right? So it cannot save energy. However, if we combine these two myths, I will show that there's a chance that we can actually save energy substantially. So let's look at this. This is a recent work that I collaborate with Professor Mingheng Lee from Cal Polytech. So this is, we basically derive equations to look at the RO process, and there's a concept called the operation number, or he called it the design number. We actually published something similar a few years ago with many, but so the operation number is basically a dimensionless number that kind of quantify for a certain flow rate, like a permeate flow rate, what would be the membrane area, given the permeability of the membrane and also the osmotic pressure of the feed. So current RO processes is operating at a operation number of around 2. That's for seawater RO. Brackish water RO would have a very different number. So for one stage RO, you see that's the blue curve, the blue line there. That's for one stage, and then the 2 stage with the same flux, that would be the green line. So as you can see, the energy saving is around 7.2%. I mean, it's reasonable, but not too exciting. On the other hand, no, so that's the energy saving, basically the yellow region there. You have to subtract that small rectangle on the upper right from that yellow region. So it's actually a little smaller. Now, however, if you can increase the operation number to 4, which means that, let's say, if you can double the permeability of your membrane, now using 2 stage can actually save quite much energy, right? So using 1 stage with a higher operation number can only save you 3.4%, very consistent with what Manny shows in the previous slide, the analysis paper. But then combining these two with a 2 stage and a more permeable membrane can actually save 17.4%. So and there's really synergy in both membrane and configuration. With only one of them, you can actually achieve that. All right, so that's the amount of energy you can save. So this is getting a little bit like theoretical, but basically this is the principle of equipartition of entropy generation. The idea is that if your driving force is uniform throughout the system, that would be the dashed line there. So a 1 stage would be the blue one, and then the 2 stage would be the green one. So you want that area between like this real curve and the ideal curve, which is the diagonal, to be as small as possible. So here with a small operational number, the difference, the saving is basically the difference between the blue curve and the green curve. But then if you can actually increase, right, if you can increase the operation number by having a membrane with double water permeability, then the saving can be actually quite substantial. Lastly, I want to talk about what if brine disposal becomes expensive. Now, I'm not really sure about whether this context is actually real, right? So, but one context I can think about is the NEOM project, and so many of you are probably familiar. So it's a royal command that we can discharge the brine to the ocean, from what I heard, they got some hiccup in the project development. But that would be a very, very expensive brine disposal cost, right? So what is the implication on the overall plant design? If that actually happens. And of course, Megan just talked about climate variability. If we want to squeeze more water from an existing infrastructure, we're going to push the water recovery to a higher level. So what would be the implication at the process level? So, I mean, the way to look at it is just to expand this equation a little bit by adding an additional term where you basically assign the cost of brine disposal to a specific energy consumption equivalent. So here I just show you some simulated results. If we need to dispose, if the brine disposal cost is at 5 kilowatt hour per cubic meter equivalent, then this purple curve would be basically what we are facing, right? The optimum recovery would would have to be increased to around 70%. You have to kind of squeeze the RO process, to push the RO process to recover more water, and then you dispose the brine using whatever way that 5 kilowatt-hour per cubic meter correspond to. And this is for 10 kilowatt-hour per cubic meter, so you will here now looking at really high recovery RO, even for seawater desalination, if brine disposal ever becomes a real demand. All right, so how can we achieve a high water recovery using RO? Here I just used one slide to talk about just kind of the conceptual framework. So this is the brine osmotic pressure or the applied pressure. So if you have the conventional RO, you can try to push that using high pressure RO, right? Just applying a higher pressure, but then there are a lot of innovations that need to be done in order to make sure the system and the membrane can still function at this high pressure. Another way to try to approach this is to increase the water recovery, increase the brine osmotic pressure while maintaining a relatively small transmembrane osmotic pressure so that you can actually use a moderate applied pressure to push the water through. And one version of it is what they call the counterflow RO, right? OARO, osmotically assisted RO, or cascading, like osmotic mediated RO, whatever. But the idea is similar. It's similar to forward osmosis where you use a drawer solution and you apply a pressure. But there's some challenges associated with that. One is the internal concentration polarization. And Tahi just told me that it's very difficult to actually push water through the permeate channel under high pressure. And then the other version, which is what I initially wanted to talk about, was the LSRO. So here you just use a leaky membrane where you can actually push a brine through, even the osmotic pressure of the brine is higher than the applied pressure just because the transmembrane pressure is actually smaller than the applied pressure. So we did some theoretical analysis, and here just give you one scenario where you can actually achieve 75% water recovery in seawater RO by combining RO and NF. And then the specific energy consumption would be around 4.2, excluding the pretreatment and other losses. So this is just a summary. So I can see there are two major opportunities to reduce the cost of seawater RO. There's significant opportunity to innovate in pretreatment, make it cheaper by just working on pretreatment processes itself, or making better membranes that can kind of that's more robust, more resilient, even without very extensive pretreatment. And also there's still major room to improve the practical, the energy efficiency of RO processes by a combination of configurational innovation, basically two-stage RO with a more permeable membrane. Lastly, if expensive brine disposal eventually becomes a lead, then we can actually push water out towards a higher water recovery using novel RO variants. So that's what I wanted to share, and I want to acknowledge the student who contributed a lot to the analysis, and also Professor Minheng Li, who co-authored that paper that I just talked about. Thank you very much.
Hi everybody, I'm Razi from Technion. I started my lab there 5 years ago in 2019. And the focus of the research in my lab is to understand molecular transport and selectivity in dense or salt-rejecting membranes like RO and NF membranes. And based on the insights that we gain, we try to develop new processes and membranes with improved selectivity. So in the coming presentation, I will talk with you about the importance and challenges of implementing solute-solute selectivity, okay, not water-solute selectivity, but solute-solute selectivity in membrane-based desalination. And I will share with you a few research directions that we are working on to improve this selectivity. So let's start, and to understand better the importance of solute-solute selectivity, let's take a look first at the case of seawater, okay, which has plenty of salts, plenty of ions. You can see here typical ionic composition of seawater. So we usually talk about tens of thousands of ppm of sodium and chloride, the major ions. Then we have a few thousands or hundreds of ppm of calcium and magnesium. We have similar concentrations of sulfate, and then we have many other ions, potassium. We also have some ions in trace levels like lithium and rubidium, and so on. So when we take this water and run it through a typical reverse osmosis membrane, we essentially remove everything, we remove all salts, so we end up on the other side of the membrane with almost a clean solution. So if we want to use this water for a certain purpose, for example, for drinking, okay, so we need to stabilize this water again with some chemicals. We need to remineralize it to add some important minerals, which of course adds additional stage and cost to the process. So already from this simple example, we can maybe understand the importance or the advantage of having a membrane that selectively transport some of the solutes to the product. So I summarized here in one slide some of the major benefits of solute-solute selectivity in membrane-based desalination. So as I already mentioned, we can have a reduced remineralization stage, or we can even avoid it completely if we transport enough minerals. As Roy talked in his talk, okay, if we transport some of the problematic ions to the product, okay, like divalent scale-formic ions like calcium and magnesium, we can minimize mineral scaling, and then we can work at higher recovery rates. It's mostly relevant for brackish water desalination. To some extent, if we do not remove all the ions, all the salt, we can maybe work at a little bit lower pressures, okay, because the osmotic pressure development over the membrane will be lower. And maybe in kind of a side product of the process, we can also try to recover some valuable elements, ions, from the water. It is very, very challenging and hard. For example, if you want to extract lithium from seawater, the concentration of the competing ion, sodium, is much, much, much higher. And so maybe if we want to try to recover lithium or rubidium or other important ions, maybe we should start from the brine and not from the feed water, where the concentration is already a little bit higher. So we mentioned how our role removes very effectively, almost completely, all salts from water. So I think that in this context of selectivity, it is also very important to introduce the younger brother or sister of reverse osmosis membrane, which is nanofiltration membrane, that has slightly larger pores, which enable to achieve selectivity not only between water and salt, but also between two salts or two solutes, as you can see here, between a purple and orange sphere. And this selectivity, solute-solute selectivity in nanofiltration membrane is most commonly explained by two main mechanisms, size exclusion or size effects and charge effects. So intuitively, usually, smaller solutes will penetrate better through the membrane, and solutes or ions that have similar charge to the charge of the membrane will be better rejected. So if we have two solutes that differ in their size and charge, we can achieve selectivity between them, and the best example is the selectivity between monovalent and divalent ions. So you can see in this figure the observed rejection of monovalent ions in red and divalent ions in green for different membranes of decreasing pore size if we go from left to right. And we can see that for the NF membranes with larger pores, we have more distinct groups, red and green groups, which means that we can achieve better selectivity for these membranes. But this selectivity that we have in current nanofiltration membranes is relatively rough. It's not perfect, it's not precise. So if we want to improve it, or maybe if we want even to reverse it, So as you can see here, the rejection of divalent ions is larger, is higher than the rejection of monovalent ions, okay? And maybe, as I mentioned at the beginning, maybe we want to transport minerals to the product, okay? So in this case, we will need to reverse the selectivity of current membranes. So to do it, we will probably need to leverage some other mechanisms beyond just simple size and charge effect. So after introducing the importance and challenges of solid-solid selectivity, I want to share with you a few of the research directions that we are investigating in the lab, and I divided it into 3 parts. So we'll talk about smart process design, okay, to improve the selectivity. Then we will talk about how controlling or optimizing the operating conditions can improve solid-solid selectivity. And I will finish my talk with an example on the fabrication of a mineral selective membrane, a membrane that can transport minerals, divalent ions, and reject monovalent ions. And we have some nice preliminary results of this. So let's start with smart process design. And I am giving here an example of the work of Paz Nativ, who is a postdoc in Ori Lab's lab. So it was a collaboration between the 2 groups. So a quick reminder about the challenge. So reverse osmosis membrane, remove all minerals from water, okay? And nanofiltration membranes, or some of them, can remove minerals and transport monovalent ions, which is exactly the opposite outcome that we want. So we decided to combine the 2 processes together in the following way. Okay, so we take brackish water and we run it first through a nanofiltration, monovalent, divalent, selective nanofiltration that can reject the divalent ions to a side stream and permeate the sodium chloride to the next stage, to the RO stage. So after the RO stage, we get, of course, a clean solution, but then we can merge the product of the RO stage with the concentrate or the reject stream from the nanofiltration state, and by doing so, we replenish some of the minerals in the product water, and we can reduce the post-treatment step. So we tested this scheme on real brackish water in Israel, in Kibbutz Magan Michael, and we found the following benefits or results. So first of all, we achieved relatively good recovery ratios, about 85%. Of course, we achieved reduced scaling potential in the RO stage because the NF membrane protected the RO from divalent ions, from scale-forming ions. One of the main objectives here was to reduce the post-treatment of remineralization. And I think that another interesting benefit of this process is that we also supplemented the water with magnesium, which in typical desalination plate, we still do not add it back to the water. We add mostly calcium. So now we have product water with more natural composition of both calcium and magnesium. One important comment is that this treatment scheme is limited to certain water sources because of the limited selectivity of the NF stage. So in general, the higher the selectivity or the monovalent divalent selectivity of the NF stage, the more water sources can be, or this treatment scheme can be applied for more types of water sources. Okay, so I move from here to the second topic of optimizing or controlling the operating conditions to improve solute-solute selectivity, and the insights from this part are coming mostly from the fundamental study in our lab to understand selectivity. So let's start with an example of the effect of temperature, and this work was a small part of Edith's dissertation, which, by the way, graduated last week, my first PhD student. And Edith's dissertation was about the application of transition state theory to explore transport and selectivity in membranes. And according to this theory, solutes or molecules that penetrate a membrane, they need to overcome an energy barrier or activation energy. So their permeation, okay, or permeability follows what we call an activation behavior, okay? And mathematically, this permeability can be described by this equation, an Arrhenius type equation. So you can see here how the permeability, P, depends on the activation energy, EA, and the temperature. Now, in practice, the temperature, the activation energy reflects the sensitivity of the permeability to changes in the temperature, okay? And because we have different solutes with distinct or different activation energies, so each solute has different sensitivity to changes in the temperature. So when we change the temperature, we will affect different solutes or the permeability of different solutes to different extent. So you can see here an example of the case of different cations. So we measured experimentally the activation energy of different cations, and then we simulated their permeability as a function of the temperature. And you can see in this case that when we heat the water a little bit, okay, we can improve the selectivity between the ions. You can see how the gap becomes higher, especially, for example, between lithium and in pink and magnesium in blue. Is it worse to heat or cool down to water to achieve solute-solute selectivity? I don't have a clear answer for that, but I'm putting it here as an option, okay? And of course, we need to consider the outcome, okay? And the economic viability of such an increase or decrease of the temperature. But it's an option. And I want to now to talk with you about another important phenomenon that can affect solute-solute selectivity. So concentration polarization is a negative effect, and it was mostly discussed in the literature in the context of how it hinders or how it can promote scaling and fouling, and how it can increase the energy consumption, the osmotic pressure over the membrane, but it was less discussed in the context of its effect on solute-solute selectivity. So in the work of, in the thesis of Ophir, we try to show how minimizing concentration polarization is very important to achieve high solute-solute selectivity. So let me define concentration polarization in simple words. So concentration polarization is basically the accumulation of rejected solutes on the membrane surface. So now let's take, for example, that we want to separate a large solute, okay, in purple, from a pink solute, from a small solute in pink here. It can simulate maybe the separation of magnesium from sodium, large solute from small solutes. So the larger solutes, because it's better rejected, it accumulates more on the membrane surface. By the way, it does not accumulate only because of its better rejection, but also because of its higher diffusivity in solution. Okay, so large solute has a lower diffusivity in solution, and therefore its ability to escape from the surface back to the solution is lower. So eventually we have higher accumulation of the big solutes that we want to reject. So the membrane needs to face more of this solute. So more of this solute will penetrate, and eventually we will get lower selectivity. So I'm just showing one figure, for example, how minimizing concentration polarization can improve the selectivity, in this case, between magnesium and sodium. So the x-axis is the mass transfer coefficient in the boundary layer. So the higher the mass transfer coefficient, if we go right, so the lower the concentration polarization. And we can increase the mass transfer coefficient, for example, by increasing the cross-flow velocity over the membrane. So we can see that when we increase the mass transfer coefficient and reduce the concentration polarization, we see how the selectivity between magnesium and sodium increases. okay, the black curve, and the shaded area represents exactly the range of typical operating conditions. So this increase in selectivity happens exactly where we actually can improve it, okay? So concentration polarization or minimizing concentration polarization, very important to improve solute selectivity. And I want to now give you a last example of a mineral selective membrane. So I think Roy already mentioned it in his talk. It's not trivial and it's very challenging to develop a membrane that transport minerals, divalent ions, and reject monovalent ions because divalent ions are larger. So I will show you some preliminary but promising results of a membrane that we fabricated that can achieve this purpose. But first, I want to remind you that I mentioned before that if we want to achieve more precise selectivity, and if we want even to reverse the selectivity of state-of-the-art membranes, we will probably need to leverage some other mechanism beyond just size and charge. And the best inspiration, of course, comes from nature, from ion-selective biological channels. So I give here a first example of the potassium channel that exists in every living organism, including in our body. And this on the cell membrane, and this channel transports 10,000 potassium ions per each sodium ion that crosses the channel, and the channel is doing it based on due to the special binding sites that the channel has along its length. And according to the review of McKinnon from in Science from 2005, these sites actually allow a transport protein to fill ions to ensure that only the right one can pass. Okay, so in practice, these binding sites, they work on two main principles. So first, ions that get to the channel, okay, because the channel is very narrow, so they need to dehydrate, okay, they need to shed the water molecules surrounding them. And this dehydration costs energy, or energy barrier, it increases the energy barrier of their permeation. But then, after the ions dehydrate and get into the channel, they need to be stabilized by this special binding site. And these binding sites are ion-specific, okay? They can fit only with a certain ion. So in the case of the potassium channel, these binding sites, they can stabilize only the potassium ion, the naked potassium ion, and we call this interactions inside the channel compensatory interactions because these interactions they compensate for the loss of the water molecules, so the ion feels within the channel that it's still surrounded by kind of water molecules or water surrogates. And because I'm going to talk with you now about calcium and not about potassium, so I just wanted to show you that the calcium channel works on similar principles. Okay, calcium ion also needs to undergo dehydration and then be stabilized within the membrane. Now back to reality. Okay, we use in desalination, we use polyamide membranes. They are the gold standard for NF and RO membranes, and these membranes are based on, or they are fabricated by the famous interfacial polymerization process, which is a reaction between two monomers, one monomer in water phase and the second monomer in organic phase. This reaction takes place on top of a porous support, most commonly UF membrane. So the reaction, these two monomers, they react, they meet each other in the interface between the water and the organic phase, and they polymerize very fast to create this well-known cross-linked ultra-thin polyamide layer. And you can see here also this famous SEM figure of the polyamide layer, okay, the ultra-thin polyamide layer on top of the polysulfone. So in the context of selectivity that we try to achieve, we can already understand that it's very high it's very hard to modify and to adjust the membrane to have these delicate binding sites, okay, because the tunability of this fabrication process is very limited. It's very limited. Okay, it's a polymerization that takes place very fast, and it's very hard to control everything in the angstrom scale. So many people actually, they try to move and look for other materials, more precise materials with a more defined geometry, like graphene, like carbon nanotubes. And we decided to stick with the polyamide. And in Alex's PhD work, we try to answer the question if we can actually make polyamide membrane ion specific. So we tried to modify the interfacial polymerization process, and we did a lot of trial and errors of different additives and concentrations. And specifically, we also added, for example, calcium chloride or calcium, with the purpose that maybe if we will fabricate the membrane in the presence of calcium, okay, so the polymer, when it's forming, maybe it will be arranged around the calcium to form kind of coordination sites in the polymer, okay? So it's kind of, I don't know, self-learning or imprinting the ion during the fabrication. And one of the purpose of the additives that I mentioned there is to promote this formation of coordination sites. So I want to show you some interesting results, okay? So first, let's look at ion selectivity or salt selectivity for different salts and for three types of membrane. We have in blue, we have control polyamide membranes that we fabricated regularly. Okay, we have one membrane that we fabricated with additives and in the presence of lithium chloride, and another membrane that we fabricated with additives and in the presence of calcium chloride. So let's take a look first on the monovalent salts. So you can see that the rejection, the salt permeability of monovalent salts, okay, on the left side, you can see that it actually, the salt permeability goes down, which is a nice byproduct for our purpose, okay? And if we move to the divalent salts on the right, we can see that the salt permeability of magnesium chloride and calcium chloride with the addition of calcium to the fabrication process goes up, okay? And these results are reflected also in the salt rejection. Okay, so here the x-axis is the type of membrane and the y-axis is the rejection. And we can see that for the three monovalent salts, the rejection goes up as we move from control to calcium chloride membrane, and the rejection of calcium chloride and magnesium chloride goes down. Okay, and if you notice, we also succeeded to reverse the selectivity between monovalent salts and divalent salts. I think this membrane is, maybe we can consider it type of dense NF membranes, and it can already maybe be used in some types of brackish water, okay, to remove enough sodium chloride and permeate minerals to the product. And these days we are working also to make this membrane also available for RO applications, for example, for seawater. So we try to fabricate a membrane with sodium chloride rejection above 99% and some permeation of calcium chloride and magnesium chloride. So, and as I already mentioned, beyond except for the applicability of this membrane, I think that scientifically is very interesting because we succeeded to reverse the intrinsic selectivity of polyamide membranes. So with that, I will move to the last slide. Three takeaway messages. So solute selectivity becomes very important in environmental sciences, including in desalination. In order To obtain high selectivity, we need mechanisms to employ mechanism beyond regular size and charge effects. And the main challenge that we try to overcome is the limited tunability of current membranes to achieve these delicate interactions that are required to achieve selectivity. So this is the last slide. And thank you. Would like to thank to my group members, to some funding agencies, and to you for listening.
All right. I can say good afternoon already. Good afternoon, everyone. My name is Pei Xu. It's really with a great pleasure I come to present, actually continue to present what Razi started, is the solute selectivity of the membranes. But we use a different approach, that is electrodialysis membranes. And I want to acknowledge my co-worker, Dr. Huiya Wang. He is also a professor at New Mexico State University. New Mexico State University is a land grant and space grant public research institution. It is all the way down the south of United States. If you drive from I-25, that start from Canada, the end point is Las Cruces. That is at the triple point of New Mexico, Texas, and Mexico. Las Cruces actually is a perfect place to do the research on desalination and the water reuse. If you look at the map, we are very close to El Paso. El Paso operates the largest inland desalination plant in the United States for brackish water desalination. And they also is designing a 10 million gallons per day direct potable water use project in the United States. So they are very pioneering. So we collaborate a lot with El Paso Water. And also we are very close to Bergendorf. So what is Bergendorf? That is federal funded research facility called the Brackish Groundwater National Desalination Research Facility. They have all kinds of brackish water and an RO concentrate. We can do pilot testing there. So this is a great place to do research. And New Mexico has very similar climate as in Israel. So we have already developed a long-term collaboration with the Israel companies and such as Ariel University and Tauya Agriculture Solution and NDRIP to develop the technologies on desalination, membrane scaling control, and also water-saving agriculture irrigation systems. So, as I mentioned, New Mexico is an arid state. It has the annual precipitation of less than 15 inches. And it is also the second largest oil-producing state. And I think Amy talked about the water-stressed states. New Mexico is ranked the #2 most water-stressed state in the United States, followed by Arizona. But Colorado is also here, Nebraska, California, and Idaho. That means that we use more water than we receive each year. That causes the depletion of the groundwater and the surface water for reuse. And let's see. So I talked to the Rio Grande project with Dr. Adin. Rio Grande, actually, it is a river, flows from Colorado to Las Cruces to El Paso, and then to Mexico. Actually, that is a highly water conflict area because of the limited fresh water supply, and the Bureau of Reclamation built a elephant-built reservoir that captures the Rio Grande water. The water is only released during the irrigation season right now. And this is a very limited water supply. You can see that this is a picture of the elephant-built reservoir. In the 1994, we have plenty of water, and in the 2013, very limited water. I just look at the water level in the reservoir. Yesterday, it is only 7.4% full. So you see that we are really lack of the water supply in this region. On top of it, right now we are having a lawsuit between the Texas and the New Mexico. Basically, Texas is suing New Mexico, saying that New Mexico pumped too much groundwater. That is hydraulically connected with the Rio Grande, because Rio Grande is supposed to deliver the water to Texas and then to Mexico. So Texas estimated the water damage is about $1 billion. And right now, it's the case in the Supreme Court. And it's very clear that New Mexico and also in our southwest region of United States, we need to develop alternative water supplies. So this is very critical. Regarding alternative supplies, we can have municipal wastewater for reuse, brackish water for desalination. We can also reuse the industrial wastewater, such as the produced water generated from the oil and gas industry. And the industry standard right now is to reuse reverse osmosis to remove all the contaminants and then generating the drinking water for reuse. In this process, we also generate the concentrate. The question is, can we develop other treatment technologies if the purpose is not for the drinking water use? For example, if we do agricultural irrigation, do we need to desalinate the water to very pure level? So this is the talk that I want to talk about, is to use selective electrodialysis to generate the water for agricultural irrigation, for concentrate management, and also for resource recovery, such as lithium that Reza also talked about. Electrodialysis is electro-driven process. So we have the cathode that is negatively charged, the anode that is positively charged. Then in between, we put the repeating cell pairs with the cation exchange membranes and anion exchange membranes. When we apply the electrical potential, then all the cations pass through the cation exchange membranes, anions pass through the anion exchange membranes. So we got the desalinated water, we call it dilute. If we can modify the membrane surface, for example, we only allow the sodium to pass through and the chloride to pass through, we left the calcium, magnesium, sulfate, those divalent ions in the product water, then this water will be perfect for irrigation with reduced sodium concentration, chloride, and the partially remove the salts. So that is the concept we developed. We call it ion switcher. So ion switcher, basically we switch the ions in the dilute stream and also in the concentrate stream. In the concentrate stream, we have low hardness, but higher salinity because it is a concentrate. And then in the dilute stream, we have low TDS, but higher calcium, magnesium, and sulfate. So this product water will be good for irrigation. And the concentrate with low hardness will be good, for example, for cooling tower water makeup, and it can be used for the wetland. In this case, we can achieve the zero liquid discharge. That is the ZLD process. Now let's look at, good concept, but do we have the membranes to do this work? And right now there are very limited membranes, the ion exchange membranes in the market. Neosepta membranes are the primary ion exchange membranes in the market. They have very good selectivity regarding the ions, solute separation, but they are expensive. The reason is they're limited manufacturer capabilities, but the market on the exchange resins right now are very high. So it's pretty expensive. And then right now we are working with Veolia Water. They also manufacture the ion exchange membranes, but we need to develop the membranes, making the coating ourselves. And the cost of Veolia membranes, ionic membranes, are moderate. So we started with the cation exchange membranes. So the membranes has a functional group of sulfonic acid. So it is negatively charged. But we want to reject the divalent ions, so we coated the with a cationic polymer. It's called polyacetylenimide, like PEI. So this is positively charged, and then there is electrostatic repulsion to reject the divalent ions, calcium and magnesium, so they can stay in our product water, and then we will allow the sodium to pass through. So this is the process. And then regarding the science. We want to know what happens on the membrane surface. So we did the membrane characterization. We have a series membrane characterization method. Here, I just want to show that electrical impedance spectroscopy results. So at the different frequency we applied, and then we can model that the diffusion boundary layer, electrical double layer, the modification layer, and also the membrane regarding their electrical impedance. And then we can calculate the transport time of the different ions through the membranes. We also measured the zeta potential of the membranes, and then we can see that the CR67 membrane is the blue membrane. That is a regular membrane before the coating. And after we coat the PEI, that is the CR671 membrane, that is the red membrane, you can see it becomes positively charged. That means we did successfully coat the membranes with the PEI. And this graph is the bold plots of the EIS, and it shows that the impedance of the membranes and as a function of the frequency, applied frequency. And the upper right figure shows that the electrical impedance of the sodium chloride solution, because we want to remove the sodium from the water at a different concentration from 0.01 to 0.1 to 0.5 molar sodium chloride. And you see a bump, a peak. That peak shows the preferential transport of the sodium. And based on the frequency at 8 hertz, we can calculate the transport time is about 20 milliseconds. So in 20 milliseconds, that the sodium passed through the membrane. And then when we look at using the calcium chloride as a solution, then we calculate the transport time is about 8 seconds. So it is much slower than the sodium. That means this membrane can preferentially transport the sodium from the solution. And when we mix the sodium with calcium in that solution, that's the natural water would have, then we found that the sodium transport time reduced, but it's still faster than the calcium. So with that, we started to do the bench scale testing, and then to treat the municipal wastewater, brackish water, and the RO concentrate. We found that the operating condition actually is also important. With increased current density, and we found the non-coated membrane will initially have very high rejection of the calcium and the magnesium. So that means calcium, magnesium transport through the membrane. We don't want that. But after the coating, the selective membranes actually have very stable selectivity, and then the sodium can pass through the membrane, so that is good. And after that, we did all the pilot scale demonstration project at the Scottsdale Water Campus, treating the tertiary effluent of the municipal wastewater, and also we did the pilot testing in the K. Bailey Hutchinson Desalination Plant, treating the brackish water and the RO concentrate in Texas. So these are the pictures of the pilot testing development, and our students are working with engineers from the Veolia Water to do the membrane coating on site. Again, this graph, it shows that the current density has significant impact on the selectivity. At a lower current density, such as 0.5 milliamps per centimeter squared, that we have the preferential selectivity of the sodium over the calcium is about 12 times better. So that is good. But with the increase of the current density, the selectivity reduced to about 2. And we also compared the salt rejection efficiency of the selective membrane and the normal grade membranes, and they are very comparable. Based on the pilot scale testing results, bench scale testing results, we also worked with Veolia Water and the Corollo engineers. We did the techno-economic assessment and also the mathematical model simulation of this process. And this is a summary table. It shows if we treat 1 million gallons per day reclaimed water, simulating the Scottsdale Water Campus treatment plant in Arizona. And right now, the baseline is to use the UF plus RO to treat that water. And the goal is to reduce the sodium concentration from over 200 milligram per liter to about 100 milligram per liter for agricultural irrigation, and also partially reduce the salt from 1,200 milligram per liter to about 500 milligram per liter. And then we did the different scenario using the WASIS modeling and also in combination with pilot scale results using the normal grade membranes and the selective membranes. We found that if we use the selective membranes, the capital investment is a little bit higher, about $6.5 per gallon per day product water flow, because we operated at a lower current density, so the membrane areas would be larger, so we have a higher capital cost. But the operating cost is only $0.8 per 1,000 gallons of water. So that is 26% of the cost reduction as compared to the current business baseline UF plus RO. Also using the selective ED, we can get higher water recovery. For the RO, it's about 88% overall water recovery. Using the selective ED, we can get 94% of water recovery. So that is very promising. And in addition to the cation exchange membranes, we also did modification of the anion exchange membranes to selectively transport the chloride from the water and let the sulfate to stay in water. And then by adding the polydopamine and the titanium dioxide or graphene oxide, we can get a good selectivity. And at the same time, the energy consumption also improved significantly by 2 times of improved energy efficiency. The next one is lithium. Everybody is interested in the critical minerals, lithium recovery. So we also use the CR67 membranes that we just modified, use the PEI. Right now, we modified with the crown ethers, because crown ethers is a ligand of the alkali ions, and then it will favor the selectivity by forming the host gas complex with the target metal ions, that is lithium in this case. And then for the crown ether, there are different types of crown ether, 12, 14, 15, and 18. They all have different size of the cavity. So in this case, we selected, we evaluated the selectivity of the lithium and using the different types of the crown ethers. And we expect that the mechanism would include the size sieving, because the crown ethers have different size. And then there is the electrical static repulsion to reject the lithium from the magnesium. And also this can change the hydration energy of the membranes. So regarding the membrane coating, first we coated with polydopamine as a natural glue, and then that can also react with the PEI, polyacylanimide, and also the different types of crown ethers. At the end, we also use the BT as the cross linker. So this is a layer by layer deposition of on the membrane surface. And then this is the zeta potential of the membranes. We coated the different layers. And basically the blue, deep blue color shows the zeta potential of the 15 crown ether coated membranes. That is very positively charged. So we expect it will have a better repulsion against the magnesium and the calcium in the water. And again, this is the electrical chemical impedance spectroscopy, and we characterize the transport of the ions at a different frequency and look at the transport in the different layers. And I want to point out to the upper left graph, you see it is a dark blue color. There is a peak. That is a peak of the lithium transport through the modification layer. And then we can calculate that the lithium transport time is about 8 milliseconds as compared to the sodium that is 20 milliseconds and the magnesium is 8 seconds. So that means the membranes are selective against the separation of the different solutes. Then we conducted the bench scale electrodialysis experiments to look at the selectivity of the lithium against the magnesium. In this case, we found that the selectivity actually can be increased by about 30 to 45% between the lithium and magnesium. And of course, the current density also played a role. With higher current density, the selectivity actually decreased. This is the same between the sodium and calcium. We also looked at the selectivity between the lithium and the sodium. We found that the selectivity actually is lower when we compare between the lithium and the magnesium. And the selectivity is only about 4 times improvement. So there is a reason. The reason is sodium is also monovalent ions like the lithium. So the mechanism of the selectivity for the lithium with other ions is the first we measured after the coating of the membrane. We reduced the water uptake. That changed the hydration effect of the membranes and reduced the impedance of the membrane. And also the lithium has lower hydrated energy and the lower cation water distance than the magnesium, so that's why we have a selective removal of lithium from the magnesium. Also, the PEI coating electronically repelled the magnesium. We also did the ATR-FTR. It shows that the magnesium has a strong bonding capacity with the membrane, and then that's basically hindered its transport of the magnesium from the membrane. Okay, so the conclusions. We think that the electrodialysis is a very promising technology to enhance the solute-solute selectivity, especially we can selectively remove sodium and chloride from the water, so this water will be more cost-effective for agricultural irrigation. And then we can also use this technology to recover resources such as lithium from the brine or the water solution. But there is still improvement we want to do. The first is we need to understand how to further improve the selectivity in the brine condition, because when we have higher ionic strengths in the solution, the selectivity actually reduced. And also the long-term stability of the membranes during, if we operated for a few years, will the coating layer still be there? Can we recoat the membranes, to recover the selectivity? Also, right now, as I mentioned, that they're limited the membranes in the market. And can we further develop the new membranes that has lower cost and the higher selectivity, and basically they can operate it for a very long time? So that is the takeaway message. I want to acknowledge all the PhD students and the postdocs working on the sodium selectivity membranes, including the Milian and Guan Yuma, Xue Song, and Wen Binjiang and Lu Lin. All the lithium work is done by Xiaochun Yin. She is a PhD student working with Hui Yao. And I'm also very grateful for all the funding agencies like Renew It. We did a lot of work funded by Renew It, by the Bureau of Reclamation, and the NAWI as well. So we also work with El Paso Water and the Veolia Coral Engineers and the Scottsdale Water Campus. With that, I'll be happy to conclude this presentation, and thank you so much for your attention.
So today, I'm going to provide you with a new technology or new area of science that I introduced to water desalination in membranes. And this is a nanoplasmonic sensing, basically because I'm working so many years on fouling control, and we didn't have any work on fouling this. We're not going to have any fouling work in this, or maybe, I don't know, any any fouling work that is going to be on this symposium, I will provide you some of the new results on using nanoplasmonic sensing for fouling control, basically prediction membrane fouling. And I'm going to compare it just to provide a certain small overview on current methods for RO membrane operation desalination. So when you talk about the Israel case, large-scale desalination plants provide 65% of the drinking water from seawater and another about 10% from brackish water. And this is an old slide, but still valid. In the next few years until 2050, the effluent source, it would be a major source for water, and not yet, it hasn't been yet decided, but it might be used also for desalination. But definitely there is a big water source from effluents comes from wastewater. We also big source for desalination, of course, will come from seawater. Both sources are, of course, are a source for desalination plants in the next 20, 30 years. This is also quite old research, but still valid. Reverse osmosis is the solution current for the world water scarcity, and we can see that both the seawater and both effluents will increase water availability, and we should consider wastewater as a resource. Quite long ago, that was the conclusion. And when we talk about municipal wastewater, effluents, and fouling issues, we have a variety of ingredients in effluents. We have, of course, the term of effluent organic matter that contains a variety of organic compounds that comes in overall concentration of about 8 to 10 milligram per liter as dissolved organic carbon. When they come in the effluent, that further will go for water use and to treat. Mixed organic matter, trace organic compounds, and of course salts. And the major problems of desalinating this water is basically microbial biofilms, membrane biofouling, eventually contaminating the membrane modules, accumulation of fouling in the module, and also cause telescoping and destroy of the actual model itself. And this is also a slide that I saw is the third time citing this paper. When we talk about seawater versus osmosis desalination, we have to also look into robust pre-treatment and monitoring, because eventually this will affect the robust operation of the plant, no matter what the plant, how the plant will be energetically will be efficient. Comparing between plants have shown that the actual operation and downtime of the plant because of fouling issues, cleaning, some modules that doesn't work, replacement of modules, eventually mix all this calculation and increase the levelized cost of water. Eventually, there are a variety of pre-treatment processes and fouling control, disinfection, coagulation, granular media filtration, membrane filtration, additional of anti-scalants. All of those eventually remove a variety of components to reduce fouling, to reduce scaling, to reduce biofouling, and so on. And there are recommended seawater quality characterization that contains certain numbers for what we call a silt density index. It's a measurement of measurement. I will talk about it later. Basically, provide a certain information about the colloidal fraction in the water, and the filterability of water through a porous membrane, turbidity, iron, TOC, manganese, silica, free chlorine, oil, and grease. And the question is now, do we really have, after pre-treatment, the best quality control that we could, that the water that comes into the actual desalination stage will be an excellent water. It's like preparing the water that eventually the membrane downstream, the models, the reverse osmosis membrane models, will be operated as long as they can. In fact, if solely salt and water will come in, they can work even for more than 5 years. They can work for 7 years or 8 years. And if we talk about a common desalination plant in Israel that contains between 25,000 to 30,000 modules, multiply that by $500 per module, that will cost $15 million. That this is the most expensive part, the most consumable, or a part in the plant that eventually will be destroyed, and we need to replace it once in a while. And if we clean the membranes all the time with harsh chemicals, because of fouling, we reduce their time span, and that will increase a lot the cost of the operation. So currently, there are a variety of methods, but most of them are focusing on colloid, on how much colloids remain after pre-treatment, and what is the pre-treatment efficiency with relation to colloids removal. And we talk about that variety of methods. I will not focus on them too deeply. There is what we call the UF or MF modifier fouling index. It's modeling the clogging of the rate of clogging of porous membranes, either UF or MF, either in constant flux or constant pressure. Another methodology is the silt density index that works in constant pressure. And there is also online methods, that the online turbidity meter and the online SDI device eventually will provide a certain measurement for a minimal, I would say, quality of the water that comes into the reverse osmosis membranes. There are also the variety of simulators, commercial simulators on or either a reverse osmosis desalination side stream or modules. One is called the NORIA. It's the reverse osmosis spotlight. It's located inside the reverse osmosis module, provide relatively late response, and focus on mineral scaling. Another one is a certain black box, a Vista black box that mimics real conditions, or hydraulic conditions. It's a very realistic RO fouling prediction device, though it could provide an answer that is quite late. Another device, or certain devices are operated by Professor Yoram Cohen in UCLA, and there are probably a few others. I just picked up the most common one that I could find in the internet. But when we are talking about reverse osmosis membrane fouling, that starts at initial adsorption in a molecular scale in the threshold phenomena of adsorption of organic dissolved carbon. Eventually, the question are all those predictive methodologies can monitor those interfacial processes that happens in tens of nanometers from the membrane, and commonly those material that adsorb to the membrane already create a certain flux decline and provide a certain conditioning film for further material to stick, colloids, bacteria, and other things. So I'm going to introduce to you a certain, you probably have heard about it. It's the plasmonic phenomena that was found, not scientifically, but was found in the Roman Empire 400 AD by producing what we call the Enon cup that is located in the British Museum. It's the Lycurgus cup, that eventually when you are shining a visible light on it, the adsorption component allows only large wavelengths to be transmitted, and the red light color to go through. And you can basically have inside gold and silver nanoparticles that resonate the green light. And that scattering component dominates in allowing the green color to be reflected. So this is the cup when you are reflecting a visible light from outside. This from the inside. This is the red light passing through. And basically, the Romans were basically synthesizing this from a material from gold and silver by certain chemical process that by trial and error they basically had nanoparticles inside the cup. This cup was reproduced by Dutch in a certain Dutch university. I don't remember when, in 2021, using those nanoparticles of silver and gold. And this is the cup. And basically, the principle is that you have certain nanoparticles in a certain geometry of commonly for visible light also noble metals. And you could see that you would have a certain creation of a electric field and a magnetic field perpendicular to it that resonates in a certain wavelength once you are shining a visible light wave through the nanoparticles. And that if you would put this nanoparticles between two silica, or for example, silica covers that will protect it, eventually materials that will absorb close to those nanoparticles will affect the dielectric constant in the close to the material. It will alter the refractive index that is directly related to it and affects the real time. We can basically study in real time the light extinction change caused reflected from the nanoparticles. And this shift in extinction maximum is basically being changed according while certain material is absorbed too close to those nanoparticles. So we have this magnitude of the shift that we have here that we follow during a certain interfacial process close to the nanoparticles reflects can provide information about the material properties adsorbed close to the nanoparticles, such as the mass, the concentration, the conformation if it's long molecule structure and thickness. And it is so accurate because the actual change is exponentially affected by related to how many atoms of a certain adsorbed material close to the nanoparticle. The applications that are known today that are found in the literature for the last 20 years is biosensing, looking into lipid bilayers, looking into molecular organization, and also looking into diffusion into porous films, and that can enlighten us that we can even use this technology to look into transport of certain components through porous media that we will build upon on top of such nanoparticles, and that for future research. But I'm not going to. First, let me show you what we have so far. And when we have this, we constructed uncoated using a certain uncoated commercial material. Even though now we're approaching the possibility to produce it ourselves. And we condition the surface with a hydrophobic uptest layer, and then we could spin coat it. We could spin coat it on a nylon, or with the amine group that we have at the end of the uptest layer. We started to do even interfacially polymerized cross-linked aromatic polyamide that we have a coated layer on top of the nanoplasmons. And we can basically sense the shift in the shift of the resonated light because of those changes, not because of any fouling or any fouling experiment, just because of those changes. And then we also study sensor sensitivity by absorbing, running through the sensor different concentration of ethylene glycol solution just to measure the sensitivity and to see if the sensor is still sensitive. And also we do a surface characterization of the sensor just to see that we indeed were coating it. And eventually, the actual first experiment we did is that we used effluent organic matter, we fractionated it to 6 different fractions with different hydrophobicities and polarities. So we have 6 materials, 5 materials in the original material with similar organic carbon concentration. And these results basically, those are from Stanford, from Megan's laboratory, when I was working in the lab 2 years ago. And basically, if you take when you play poker and you open 6 cards, and you have 6 cards, and all of those cards, with these 6 cards, you basically have 6 fractions that you use for fouling experiments, and you take those 6 cards for absorption of the nanoplasmonic LSPR sensor. So you had your 2 groups that one is causing less fouling, and 2 other groups that cause more fouling. Those are the 2 groups. These are the more fouling, the red ones, and the blue is the less fouling. And the least fouling fraction, which was a transphilic acid, it doesn't matter right now, was this one. So we got a very nice correlation for this relationship. So we didn't really aim to do anything that relates to sensing stuff back 2.5 years ago, or 2 years ago. And eventually, the next step was to see if we really can do fouling prediction using the model foulants and effluent organic matter, comparing to other methods. And I don't know, the slide, maybe you don't see too well from where you sit down, but basically here you have 4 different fouling experiments with humic acid, alginate, secondary effluents, and athlete proteins powder that you dissolve in water, and you have all kinds of things inside, and you buy it in the supermarket and use it as a model foulant. And then we did also the experiment for the LSPR experiment, and we compared the final absorption, the final reduction of the flux, and we nicely compared that also to some trying to predict it with some people are doing QCMD. Who are doing this? Some people are doing QCMD results to see what is the hydrated mass attached to the sensor, what is the maximum frequency shift. We also did the experiment, the silt density index measurement. Basically, if you filter a certain amount of water, you measure the rate of clogging microfiltration membrane. And we compare how all of those results may predict fouling using those model foulants. And the actual nice relationship using LSPR mass surface concentration provide us nice relationship both to the RO flux decline and the hydraulic resistance that we calculated caused by those foulants on the membrane. So this is make us feel good, and we're still continuing doing this work currently with seawater. I don't have any result that I can present right now with seawater. And if I still have time, I will also talk about prediction of UF membrane fouling, or ultrafiltration membrane fouling compared to RO with LSPR, because in this case it's slightly more complicated. We used two biofilm reactors, and we extracted those extracellular polymeric substances, one from fixed bed bioreactor and the other one from fluidized bed bioreactor. And we had 2 types of EPS, or extracellular polymeric substances. Basically, it's called EPS. We extracted the biofilms from particles, and we did study the absorption or the elevation of the transmembrane pressure and the constant flux of ultrafiltration membrane under different aquatic conditions. And eventually we compare that to the LSPR results with these two reactors, and the correlation was quite good. Even though it was nice results, it was of course made sense because the membrane molecular weight cutoff was smaller than the actual size of the EPS measured by gel permeable sheet chromatography, and that made sense because we had this. This could explain that most of the material accumulates from the outside of the membrane and of the ultrafiltration membrane, and that could explain the results were nicely explained by the LSPR. What happens if extracellular polymeric substances or any foulants would be smaller than the molecular weight cutoff, that it would accumulate inside the pores? Then we'll have some limitation. And the EPS behavior in the UF ultrafiltration confined environment will dictate fouling. So that eventually conformational changes of foulants and dehydration and hydration of foulant in the confined environment of the ultrafiltration membrane will dictate the fouling behavior of the ultrafiltration membrane, as we saw in the past. And for that, we use the hybrid QCMD and LSPR analysis, in which you can basically differentiate two major fouling characteristics on a surface. One is the hydration of the foulant, that you can basically use this information from a QCMD result, that you can get hydrated mass, and you also can get viscoelastic properties. But the LSPR eventually provides solely the dry mass material that affect the refractive index, or the change of the refractive index near the surface. And from that, we deduce the dry mass concentration. I will not go to the calculation right now, because there are some parameters that we need to of course, evaluate and eventually calculate how much dry mass is on the surface. And eventually, we prepared a sensor that was also a QCMD sensor and an LSPR sensor, basically a hybrid measurement. And we could explain, for example, why at high pH you get a certain, when you are running fouling experiments of a membrane bioreactor, at high pH you have a decrease of permeability, and at low pH you get elevation of permeability because of change of conformation that we got in an LSPR measurement for the change of the amount for the reversible change of the amount close to the LSPR sensor. We did the same experiments with control experiments with alginate that was smaller than the molecular weight cutoff of the membrane, and we got the same results with that we could explain solely by change of conformation inside the pores using alginate. When you absorbing alginate to the membrane pores, you get elevation of the transmembrane pressure, and now you have alginate inside and start to wash the membrane with double distilled water, and the alginate just swells inside and cause elevation of the transmembrane pressure, compared to a control membrane that we modified with a positively charged moieties. This is another result using how alginate in DDW is basically clogging membrane much more than when it's in compact conformation using once you are introducing with high ionic strengths. We got this conformation using LSPR, even though we got a decline here for the amount because it's a flat, it's not confined environment, just a flat sensor, but we had this elevation, or here a reduction once we are reducing ionic strength, elevation of the amount to the LSPR reading, once we elevate the ionic strength, and so on. Then eventually we got no material on the sensor because it was washed away. So our concluding remarks is just 3 concluding remarks. One is that LSPR was applied for the first time in membrane research, and it was successfully, in contrast to QCMD and SDI, we could start to see a repetition of prediction for RO membrane fouling, and that LSPR can predict UF membrane fouling once the molecular weight foulant is bigger than the molecular weight cut of the membrane. If it's smaller, then we need to look into conformational change in hydration and so on, the effect of what happens with foulant in confinement environment. So thank you very much. Our lab is much bigger than this one. These are just the ones that were willing to take the picture. So, so thanks.
I think we will have some time for questions. I mean, yeah, about 5 to 10 minutes of question until the reception. So please feel free to ask questions.
So many, yeah, please.
So just in general, how do you compare this kind of photonic approach versus electrochemical approach like EIS? Like EIS, how do you compare this to EIS? Yeah, like pros and cons.
EIS is also a good measurement, because I think we didn't do EIS for those, but it could be useful. But I think we didn't analyze that, but it might work in the same way. We didn't compare to EIS yet, but yes.
What will you do with science?
Yeah, it's a good question. What do we do next? What do we do next? How do we imply this result? So the idea is that, first of all, we have some different projects. One of the projects is to look into the efficiency of pre-treatment of seawater desalination. And what do we do is that, for example, if you see that some material escaping the SDI and you're able to recognize it with your sensor, you may need to see what is wrong with your pre-treatment. There is a variety of answers to that. But again, this is a matter for the next step research. But of course, it needs to be, yes. Yes, Megan.
Moshe, it's so fun to see how far you've taken this. So congratulations, first of all. I just had a question about using this as a sensor. It's a really interesting application, and I think very promising. Yeah. That's the whole idea. We have the money for the Israeli Innovation Authority. We will be, hopefully, proof of concept of a sensor that might be used as a sole sensor or integrated to a certain further device that will cover the monitoring of water that comes to the RO. I guess my question, though, is that you have a really diverse set of hydrodynamic conditions. You have a very diverse set of hydrodynamic conditions and foulant concentrations in your actual membrane modules. And whenever you do sensing in a slipstream or in the actual stream that's being fed, it seems very difficult to actually match or pair those hydrodynamic conditions and foulant concentrations, given that you're concentrating the feed. So I'm wondering if you can comment on whether you've looked specifically at how well the hydrodynamic conditions in the current LSPR module match those in the membrane module, and whether it might be worth modifying the.
So definitely the hydrodynamic conditions are all the same. We just studied. Yeah, okay, this one. So definitely it's not the same hydrodynamic, it's completely different. We just studied currently the interactions of what is the actual affinity of certain foulants in the water to a similar material as the membrane. Those systems that mimic real conditions basically commonly provide you the alarm when it's too late, because when they're fouled, a lot of water already got into the membrane, into the plant. The idea is to place this sensor at different locations in the plant later. just to see and with different water that went through a variety of recoveries. And so this is also, currently we're just in the initial step to see that in a lab it can work. But you're right that eventually further adaptation will need to be done. Later on, probably some engineering that relates to hydrodynamics will need to be done. But everything is feasible. It's just engineering. So currently, it's just a proof of concept. And according to what I have been exposed and also some trials we did in the lab for other methods, I had the feeling that after 17 years, it might be something, really. Or at least something I could get money for.
May I just add something about that? I think one of the direction is going to some kind of calibration curves, doing a lot of experiments to see how different foulant behaves under different conditions, and then you don't care about the hydraulic condition because you do in parallel RO experiments, and then even go further and do some artificial intelligence that can help you to know what's going on under a specific condition. And then if there are some things, because the amount of the foulants perhaps is not endless. Yeah, so you can do the major ones, and then you can also know that if something is completely different, then you put it into the information, and then you can know that something different happened. So this, I think, is the next step after the first step of just establishing the technology.
Yeah. I have something to say about sensitivity, but I don't see that the slide is not there. Is not. Can I see? Can I get my presentation back? No, mine. This the presentation. Oh, never mind. It doesn't matter. Forget it. You want to go? Yeah. Please, Amy.
I was going to ask you, but I think you were finishing an answer. But I was going to ask a question about one of your slides.
Okay. Yeah. This is what I would like really to show something about sensitivity. There is something very interesting about sensitivity here. Okay. Perfect. Before your questions, Amy, I want to say something about sensitivity, because I have. This is one of those things that made me feel nice about the results, is that when you look, because you don't, one second. When you look at the results in this part, the elevation, the mass surface concentration attached to the sensor, this amount is solely by change of 0.3 nanometer of the actual sensor. Eventually, you can sense up to tens of nanometer that you can get. So the sensor can accumulate a lot of foulant on it, much more than what we already sense. So, and that material, if much more foulant can be accumulated on the sensor, and we can still provide information, then it might be able to be used for a long time in reality. So this is just a speculation, but again, yes, please.
So
I was just going to wait till the end and ask a question, so maybe it's the end. Like your slide where you showed future sources of water supply in Israel, would you pull that back up? It was your first or second slide.
Oh, okay. That's the reproduction, yes.
Yeah. Yeah, this one, okay. So is this saying potable reuse? This is water consumption.
It's always the matter of the Israel Water Authority to decide, and in Israel it's very well organized. It's not like here.
It's irrigation.
So the Israeli Water Authority eventually will decide what to do with this amount. But this amount will definitely increase and we will need to see. But it is definitely desalination is available for using.
So is this saying the effluent is water that will be used for potable reuse?
No.
No.
Irrigation.
No.
This is all irrigation. Okay.
90% could be used for irrigation.
Okay.
Which is the entire 50% of the irrigation.
Okay.
Just one last question, because all the Israeli colleagues falling asleep, jet lagged, and we need to have reception. So one last question, Faye.
Okay, yeah. So it's really great talk. I have a question. It seems like you have already studied mostly fouling, organic fouling and biofouling. But for example, for brackish water desalination, it's mostly inorganic scaling. And also when you have organics and then it's all combined, scaling and fouling, can your method detect that as well?
You're definitely correct. So basically, if you have this a hybrid QCMD and the LSBR, we can even differentiate between, at least from the paper, differentiate between heterogenic and homogenic scaling, or happens on the surface or in the bud, very close but still in the bud, then QCM will give you data and LSBR will not. So this is one of those benefits of using hybrid QCM LSBR device.
But why don't you have turbidity measurement?
Because turbidity will provide you solely the colloidal fraction.
It will tell you something is happening.
But eventually...
Again, for this case.
Oh, for this case, yes.
For this case.
For this case, you can use turbidity, but you don't know exactly what happens on the surface when you're doing turbidity. And that's where to provide you the very close 1 nanometer scale, what actually close to the
I think it's time to close the day. Thank you, Moshe, for the great talk, and thanks for all the speakers. Yeah.